Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Hello, everyone. My name is Arnoud de Vos from European Laboratory in Learning and Intelligent Systems, ALICE in short, and I have the privilege to moderate today's session. So the success of modern AI systems has been largely driven by massive scaling of data and compute resources. However, in scientific applications where physical constraints and geometric structures are crucial, the scale is all you need paradigm shows clear limitations. So this talk with two speakers presents cutting-edge approaches that combine the reliability of geometry preserving neural architectures with the scalability demands of real-world scientific applications. And now it's my pleasure to introduce the first speaker, which is Eric Bekkers. Eric Bekkers is an assistant professor in geometric deep learning at the Amsterdam Machine Learning Lab, AM Lab, at the University of Amsterdam. His research focuses on making AI systems intrinsically capable of geometric reasoning through geometry-grounded representation learning. So without further ado, the floor is yours, Eric.
Thank you very much for the introduction. Let me try to put up my slides. Okay, there we go. Yeah, thank you so much for the introduction and for inviting me, or us actually. So I'm gonna be giving this talk, Symmetry, Scale and Science, a Geometric Path to Better AI, together with Johannes Brandstetter. We've been long-term collaborators and we know each other from our Amsterdam time. I'm still in Amsterdam, recently promoted to associate prof, so happy to share that news too. Yeah, and actually the purpose of today's talk, or my role in it, is to introduce this notion and the importance of symmetry and scale both at the same time, and to sort of, bring forward my vision towards how to advance the deep learning field beyond the scale is all you need argument. And I'm going to be coming back to this nice painting by Giuseppe Arcimboldo. So I want to start off with the state of the art in AI and generative modeling specifically, just to make a point. So this is a video generated by Sora. The prompt is at the bottom. A glass of lemonade falls and shatters. Yeah, so this is what it looks like. So what you do see is you see patterns that indeed correlate with this prompt. So you see spilled lemonade, you see a glass of lemonade. But you also see shards over there, but the physics and the order and things, so the causality doesn't add up, it doesn't work at all, but there are clear correlations between the prompt and what we see. If we look at another video, so this is also kind of cute, and if you look at it, you don't see any problem, but then you look carefully, and then you see that these puppies playing on the road, sort of they merge and integrate with each other, and then they emerge out of each other. So clearly, the notions of geometry and concept from a real world are violated. But yeah, is this, can I call this state of the art? Well, it was now almost over a year ago. So quite recently, we've seen newer models come out, even bigger, better models, but still, well, we see these disturbing, instances of what you call body horror. So these problems to date are still not solved. And so this sort of brings me to the main point that I want to make, is that even the largest systems on Earth, they struggle with representing real world concepts like physics and geometry. And so far the paradigm has been, or the last couple of years, is that of scale is all you need. That if we ever scale up our models, that at some point these problems are no longer problems, because the systems have learned to grok or to understand the principles behind the data and the real world. And I think not only this is naive because we keep running into these edge cases, I also think this approach is hampered by serious ethical issues surrounding, well, data collection and harvesting and curation, the environmental impact obviously associated with training these tremendous models as well as maintaining them, and naive in the sense that data availability is not always a given in many scenarios, such as in scientific and medical domains. So my pitch of today is not scale is all you need, but the rough summary is that of geometry is all you need. And so I'll get back to this quite often during the talk. Yeah, so I started off actually with these videos because they speak to the imaginations. They clearly show that these deep learning systems fail to comprehend and properly represent real world phenomena. But be aware that this kind of misrepresentation is widespread and it's inherent to essentially all of these AI models. So even if you have a classifier, so not a fancy generator, but a simple classifier, we've seen this problem that if we train it to classify medical data and turn the image, so this is a histopathology slide, and rotate it a bit, and then all of a sudden it would give the exact opposite classification. And obviously, so this happens, and it happens a lot, and we see that these models are just unreliable or really intolerable in certain scenarios. And well, my group has pursued a lot of these medical applications and tried to bypass this, and we just see over and over again that scale won't fix this. You always run into these edge cases, so that leads to unreliable systems. So now my research over the last, well, yeah, I know 5-6 years has been to incorporate geometric structure into deep learning systems as to make sure that these methods are provably robust due to geometric distortions and transformations, and due to a principle called equivariance. I'll explain that in a bit. But the idea is that now we hardwire geometric structure into neural networks, such that if you rotate your sample, the system will provably be robust to this and maintain its original decisions. So at least we are now able to get rid of these nuisance variables, let's say. So back to the equivariance and invariance principles, I want to zoom in on this. And this is quite prevalent, not just in computer vision or medical imaging, but in scientific domains, working with physical systems, for example, if you want to predict the energy of a system, or even more complex, try to relate geometry to function. These AI systems struggle a lot with making these kind of decisions or predictions unless you guide them, let's say, through geometric principles. So that's what I am gonna focus on now. So the idea is that, okay, so if you do that, then you can have reliable systems that are capable of solving these kind of problems. So terminology-wise, I want to make sure that we're all on the same page. So I'm going to talk about invariance. And invariance is a property of a system that says, well, if your input rotates, for example, this molecule, let's turn it upside down and then press it through a neural network, that it still returns the same output, right? So this is called invariance. Invariance says if I apply a transformation to the input and pass it through the function value stays invariant, right? It would give the same output as if I wouldn't rotate or transform the input. Okay, so this is a property that many times is required. And we now have the tools to guarantee this, right? Now, equivariance, that is an even more important property, I think, and that's as follows. Suppose now I have a neural network that predicts forces associated to these atoms. Then we want that if my molecule is now rotated upside down, that these force factors also rotate accordingly. So this is a bit more of a of a stronger property because it essentially means that geometric structure is maintained, such as the directions of these factors, they rotate accordingly. So in technical terms, it means like if I now have a function that takes, let's look over here, a function that takes a point cloud as input, and it spits out force factors, then we want, if we rotate the input, that the force factors are also rotated. In other words, there exists a transformation also on the outputs of these systems, such that we have a commutative diagram. And the fact that if such a neural network is equivariant, that means we have such a transformation defined on the output, means that the structure is maintained. I can talk about transformations of data in a meaningful way also after we pulled it through a neural network. So geometric structure is preserved, and this is really important in these scientific domains. Yeah, so this is roughly the scope of, well, group equivariant deep learning. So actually, didn't mention that much, but this talk is part of Alice's program on geometric deep learning. So we have a lot of research in Europe around the idea of incorporating geometric structure in neural networks and adapting neural networks to handle geometric data. And one of the sub-disciplines within geometric deep learning is that of group equivariant deep learning. And this is everything to do with how to handle symmetries and transformations in data in a consistent manner. And we see that in many applications, right? So we want to maybe be invariant to rotations, or we have a dynamical systems and we want to respect the symmetries of the equations that underlie these systems. Yeah, this is some abstract representation of, well, of some molecule. So this is just talking about constraints, right, that often need to be met. And this is where the equivariant deep learning field provides solutions to. At the same time, we also have that equivariance allows for a notion of weight sharing, and this is really the main factor behind computer vision that made the field leap forward in the idea of convolutional neural networks. Well, this equivariance allows to share patterns over over transformations beyond just translations to rotation, scale, etc. And beside this, our field is motivated a lot by concepts from perception, like the psychology of vision, and nature itself, where we see a lot of symmetries. And symmetries essentially means efficiency, because, well, you learn to represent things in a canonical way and able to generalize this to the whole symmetry group. So this is a bit of background to my research. Sorry, I am going to quickly go over this. I had to give like a promotion talk recently, so I'm going over my CV and my role in this. So I did my PhD in medical image analysis and differential geometry. And since then, 2018, I've been working on incorporating this geometric structure into neural networks, working on a concept called group convolutional neural networks, and then try to generalize this to all sorts of transformation groups, like Lie groups in particular, and then how to parameterize these neural networks. So there's several ways to achieve these properties of invariance and equivariance. This is a paper I'm very proud of, together with Johannes Brandstetter. So he's talking in 20 minutes or so, where we really worked out all the different methods to how to build equivariant architectures based on, well, irreducible representation theory of Fourier theory in some sense. And this later culminated in a course on geometric deep learning. So if you're interested in learning more about these concepts that I introduced, I'm going to talk about more. I put these videos on YouTube so you can watch them. It's a more or less self-contained series on how to build neural networks that respect these symmetries. In terms of the Alice program, so I now joined the directorship for the geometric deep learning program. This is a paper that I briefly want to highlight because it touches upon a very relevant debate that we still have, and that's the need for these kind of equivariances, because it sounds kind of complicated, even though it doesn't have to be like this. But the idea often is, well, why not just get more data or use data augmentations? And in this paper, we explored it deeper and showed that actually, if we train neural networks with data augmentations, then what we get is actually only an apparent form of these, an apparent attainment of these properties like invariance. And these properties and this reliability that breaks under distribution shifts. And lately we've seen more papers in this direction that theoretically prove that, well, you can only get reliability if you do something about your architectures. And okay, a bit more recent trends, this geometric deep learning tools, we've now been using them for generating geometric data like molecular point clouds or vessel trees. And this now is something that I'm going to talk about next, and that's more about how to represent data. And a trend that we see in the field recently is that of using equivariant neural fields, and I'll explain that soon in more details. And this is what I recently got a personal grant on to develop this paradigm of doing deep learning using latent representations that are still geometrically meaningful. Okay, so a lot of introduction. So this is basically what you might call, this has been part of our first wave in group equivariant deep learning, focusing on these tools that allow you to construct neural networks with these properties. So previously I said, well, I don't believe in the scale is all you need argument. You might consider that I would believe a group convolution is all you need. And actually I've been saying this a lot in my lectures, but also this I don't believe anymore. And I'm gonna explain why this is the case. I'm a big fan of group convolutions, as you might have known by now, for several reasons. Well, these group equivariant paradigms, it allows for provable reliability. It allows for data efficiently, like significant data efficiency, because now neural networks only have to learn one canonical pattern and then are able to generalize to all these transformations in the group. And you get to performance gains that you simply cannot get by just getting more data or via data augmentations. But why does this solution still not solve, why does it compete so well with, the large scale computational methods? And it's for several reasons. First of all, these equivariant methods, they struggle with scalable issues, like the complexity of these neural networks. It scales somewhat linearly with the size of the group. So for example, if you want to be robust to rotations and you discretize the rotation group with, let's say, 10 reference rotations, then your network becomes roughly 10 times slower. And it's not quite like that, but it's not that bad, but you get the point. If you also want scale or other groups, well, things just get slow. But I would argue that the main bottleneck here is that quite often we don't have access to explicit geometry. So we've seen real impact, like big impact in domains where we have access to, for example, the atomic coordinates, right? So we have an atomic point cloud, so now we can explicitly talk about a displacement of this atom to the next atom. We can talk about distances explicitly. In medical imaging, we can talk about exact rotations. But now in computer vision and other domains, the geometry is implicit. It's hidden behind the pixels, if you will. And moreover, we have to look at sort of 2D projections of 3D scenes. But still, we know that we're looking at objects that have this geometric component to it. We just don't know how to sort of compute with it, how to bring this geometry forward. And so this is bringing me to the main point of the talk, and that's actually that the essence of a concept is often geometric, but this geometric essence is not representable by current AI systems. And with that, I mean that if you look at this painting, we clearly see the concept of a face, like a portrait of a person. And we see that because of the geometric configuration of objects relative to each other. And it's not because of the texture or the color. And now the problem is that these neural networks, they typically look precisely at these pixels and their colors, but they don't have access to explicitly represent the geometric objects in this image. And this is known as the texture bias. And roughly speaking, it works a bit like this. Suppose I have two images and they might be very similar in pixel space. So the black and red pixels, they barely overlap. So there's a large distance in pixel space. And now if you build, for example, a generative model, you want to have continuity in frames and you want proximity in your generation space. And that's what's leading to the fact that these images, you want them to align as much as possible based on a metric that doesn't reflect the geometric content, but only texture and color. And that's why we get these nice smooth looking videos. But if you look closely, they're inherently meaningless because they don't represent the geometry in a coherent way. So this is just a quick summary of the texture bias. Now, my solution in this, and I show some preliminary results in this regard, is to make geometric components explicit in image data or signal data, right? So instead of looking at pixels, I'm going to make the image geometric, so explicitly a point cloud, and then do reasoning and processing of these point clouds. Yeah, so that's the SIME project, which I'll be working on for the next 5 years, and I'm now collecting a team, and some of them already started, where I really focus on this notion coming from, well, theoretical neuroscience of perception, that quite often we work with perception, and I want to know that actually an image is already a representation of something true out there in the real world, and then our brains make another more abstract representation to it. But the whole concept of reasoning is that we build up these representations that behave in a way that the world behaves like, right? And we know the world behaves according to certain physical laws and symmetries. And so that's the conceptual idea that we're following, is that instead of working in pixel space directly, we build up a representation space that is still amenable to geometric transformations and physical laws, to reasoning in this space, but also be able to tie our abstract representation to concrete perceptions in a generative or rendering format. So I'm not going to dive into the neuroscience motivation, because in the end, that's really a motivation. The core thing is that we want to maintain geometric structure in whatever things we're going to compute with. So I talked about this equivariant deep learning. Let's call it the first wave of group equivariant deep learning. So now we have all these tools, and they're accessible. The theory has been worked out. This also in the case where geometric structure is latent or not explicit to us. So now I have to talk about representation learning, how to, well, distill these representations, but then still process them in meaningful ways. So that's what I call geometry grounded representation learning. And one instance of it, and that's our approach to it, and that's through equivariant neural fields. So this is the main technical component. I just want to get the gist across. For details, you can check out the papers, of course. So this is recently accepted at ICLR. So it's called Grounding Continuous Representations in Geometry, led by David Westels and David Knigge. And the idea is as follows. So we're looking at neural fields, and neural fields can be thought of as just functions, continuous functions that take over some coordinate space. So they take, for example, an XY coordinate, you pass it through a neural network, and then the neural network spits out an RGB value, right? So it's a mapping from a coordinate to some vector value. So this function f, and that thing, since it's parameterized by a neural network, we call it a neural field. So that's simply the thing. We have an image, we fit a neural network and its parameters such that for every pixel coordinate, it spits out the right RGB value. And then we can plug in any coordinate that we want, and we have effectively obtained a continuous function. Now you could do this for an entire data set of images or signals, and then you get an entire data set of neural network weights. And in some sense, these weights, they represent the image, right? So I can use them as a representation for downstream tasks. And this is what people have been doing. The complicated factor here is, well, actually manifold, because if you fit a neural network to represent an image, you do it again, you get a different set of weights. You do it again, you get a different set of weights. So you don't have this consistency, but also there's a lot of symmetries in the parameter space that leave the output actually invariant. So that's why you have to process these with graph neural networks. But then next to this, people came up with the notion of conditional neural fields, and this solves a lot of problems. So the idea is that still we have a neural network that maps an XY coordinate to some RGB value, but now you modulate the activations in your neural network based on some vector. So you have some sort of conditioning going on. If you change this vector, then the matrices and the biases in your neural network are adapted. And thus, if you change the vector, a different image comes out. And now the idea of conditional neural fields is to train such a neural network. So we share the same weights for all images, but just vary the latent vectors, z's, to represent the image. If you want to represent another image, I only change the latent vector, but not the neural network parameters. And this leads to a bit more useful representation of the data, because now we have a vector, and a vector is much easier to work with for downstream tasks. The problem still is that now in many tests we want to reason about geometric content, and there's no way we're going to deduce from these vectors what we're looking at. And that's something I'm going to show in the experiments section, that these vectors are not geometrically meaningful in any way. They might be able to compress the image content, but you cannot really reason about the content based on this. So this concept of representing signals, continuous signals, with neural networks, it's called learning with functa, and I think it's a really nice paradigm, because this vector essentially represents a whole continuous image. Now, our approach to this is, instead of, let's zoom in. So instead of representing the image in pixel space or conditioning it on a vector, we're going to condition it on a latent point cloud. So we say the image actually is consisting of a bunch of particles, each having a position and an orientation and a description vector. And this set of particles, we can decode this via what we call an equivariant neural field into an image. More generally speaking, we typically take the latent point clouds as a point cloud in a group, in a Lie group, and consider signals over homogeneous spaces or spaces on which this group can act. But without going too deep into this technical content, the idea is now that we came up with a method to represent signals with latent point clouds. And conceptually, the idea is that, well, an image can be decomposed into, for example, two ears, which share the same description vector, but just they differ in pose, a nose, eyes, and a mouth, and these kind of things. So now we are able to assign to each image a point cloud. And we do this in an equivariant way, and this is what I mean with grounding in geometry, that these latents are grounded in the same geometry as the input space, meaning that if we were to translate or rotate this latent point cloud, the decoded image would also be rotated and translated. So this means that in this latent space, I can still think about relative offsets, distances, rotations, transformations, and whatnot. So we compressed an image into a point cloud that still allows us to talk about geometric transformations. So that's the main principle behind our idea of equivariant neural fields. Considering time, I don't want to spend too much time on the technical background, but just want to share that this method is, well, simply based on cross-attention, so transformer type parameterization, where we cross-attend between the latent point cloud and a pixel representation. So because we're converting a point cloud into a pixel representation. And conceptually, we have to condition these transformer layers, or the value transform, as well as the attention based on these geometric attributes. And that's something that we worked at in recent work on fast equivariant graph neural networks. But the point now is that we are able to decompose an image into latent particles, and each particle is responsible for generating a part of the image. Now I want to make the point that now that we have geometry grounded representations, we also have improved performances. And so the idea is, well, we have fitted a database of these representations to image data. For example, in the classic approach, we were representing an image with a vector, but now we represent it with a latent point cloud. And we can then pass it through for a downstream task, for example, in classification. So this is what we did on Cypher 10, for example. If we use the classic approach and use these vectors for classification, we got at best like 68% accuracy. And simply by switching to our equivariant neural field, so that means now geometric information is explicitly accessible, you get like quite a big gain in performances. And this is to say actually that these representations are obtained in an unsupervised way. So only we trained on representation signals, and then we use this point cloud for classifications downstream. And we see this kind of recipe also works nicely for shape representation and segmentation. The flexibility of working with neural fields is that you can represent multimodal data also in one coherent representation space. So in this unsupervised way, we trained neural fields to represent jointly 4 channels or elements of satellite data. This is for the task of flooding segmentation. So we have these 4 modalities, and based on that, we want to get a flood map out of it. So we could pre-train our neural fields to represent these data, and in a downstream task, we train a neural network to turn this latent into a continuous segmentation. And so with this neural field approach, we actually got performances that go beyond the state of the art that uses a unit, but in such a way that we do this in a continuous way. So a method in a way that does not depend on the exact gridding or pixel representation of your input data. In fact, suppose we only were to see 10% of the pixels in our satellite images, suppose there's some occlusion going on, we still maintain roughly the same performance. So our method is in that sense agnostic to the precise choice for resolution. And we also demonstrated that by training, for example, on the 128 resolution, and then tested for the case where the images were of higher resolution, and then we still got like a good IOU, or we tested on training data that comes in on a 64 by 64 pixel resolution, and we maintain our accuracies. So this shows that without any supervision on super resolution or whatever, the method is robust against these pixel variations. Okay. What I'm actually most excited about is this idea of forecasting in latent space, because this really shows that these representations are geometrically meaningful. So it's called space-time continuous PDE forecasting. And the idea is as follows. Suppose we have a dynamical system, for example, a climate model of the Earth. We want to model this. We are going to do so by representing this signal, this continuous signal, in our latent space, or geometry-grounded latent space, model the dynamics in an efficient way in this latent space. And then for every point along the time axis, we're going to decode the image to obtain a continuous movement of these dynamics. So that's actually the same set with a different picture. We have a continuous field. We know it evolves in some way. So we're going to encode it into this latent particle space, solve a neural ODE or train a neural ODE and solving using this integration. And at every time point, we can decode the solution out of it. And this works amazingly well. And I was kind of surprised by it, but it's kind of shows that we can do all these tasks now also in a more abstract latent space, which still carries geometric structure. Also here we see efficiency in terms of, we can do with only 5% of the pixel observations and still do a good job. And the recipe also allows to generalize a different type of manifolds, like do this on a sphere or on an internally heated ball. So this is also an interesting dynamical system. Going back to the data efficiency paradigm, so also here, and this is what everybody in equivariant deep learning always says, like, okay, equivariance leads to more data efficiency, and that's what we show again here. I just want to relate this back to current trends in AI. So recently, a year ago by now, I guess, this was this amazing model by Microsoft Research on modeling climate data, a foundation model of the atmosphere. And it follows a roughly similar paradigm where really it shows that one needs to work with a latent variable model, in this case, structured data, but it's still a foundation model. So there's like a huge amount of parameters. Conceptually, it does do the dynamics in the latent space and decodes out of it. And our group is currently working on doing this in a way that's geometry grounded, and in that sense, preserves the physics underlying these kind of dynamical systems with way less data and way less parameters. Okay, so that's for geometry grounded representation learning. And I think my time's up. So I just want to highlight 3 papers. I'm not going into details, but I'll be quick on this. Falling in the paradigm of the basics of equivariant deep learning. One is just I want to pitch, we have like a good general purpose equivariant point cloud neural network. So if you're interested in, trying these kind of tools, we have this paper where we explain the basics of that method. And what it provides is really a practical method and code for group equivariant graph neural networks or point clouds. It's fast because it's based on, okay, that's technical, regular representation instead of irreducible representations. And basically what it means, we don't have to worry about the precise operations that we perform. We just work with invariants or scalars, so you don't have to mess with your activation functions or anything. So it will, whatever is invariant will stay invariant, but it is way more expressive than the current, standard like EGNN. Yeah, okay, so maybe that's all I can say about it, and that we came up with a nice acronym. So yeah, Ponyta is obviously a great fire Pokemon. Now, this is actually a point I want to make. Like, if you work in generative models for geometric data, it's very important that these models inherently have this kind of notion of geometry and geometric structure. Like if you want to generate a molecule, you want to put the side chains in the right positions relative to the rest. And so this idea of being able to internally represent directional information, that's crucial in these kind of tasks. And we see that in generative modeling, like this model is not capable of representing directional information, and this one is, so our model is. And that it's a huge boost in performance. Okay, this is to show that we benchmarked it on a lot of data sets, all available in the repository. This is a paper addressing the idea of whether or not we really need equivariant neural networks. So we worked on a general purpose adaptation of Ponyta called Rapidash. It's also out there on GitHub if you want to use this and the documentation is not clear enough, please send me a message and we can help you out. But the idea behind this paper is that we studied when does equivariance matter and when not, because there's some signals coming from the field that, well, scale is still all you need. And we argue that this is not the case. And we extensively show this on a range of benchmarks that we organized on an axis of complexity. I just want to move to the conclusions to wrap things up, because we organized the paper in terms of hypotheses. And basically we hypothesize that equivariant methods are more data efficient. Well, they are. That the benefit of equivariance increases with task complexity. That's also good to know. We also show that, well, even the non-equivariant models or the non-constraint models, even if we make them bigger or scale them up, we do not get the same gains that we get with this group equivariant methods. There are tasks that do not strictly require equivariance, and so then the benefit is less obvious. And finally, we also investigate how shall we present geometric information to a neural network. And we show that actually just providing geometric content to a classifier or regressor improves performance, even if this slightly breaks the symmetries that you're after. Only thing I'm going to say about this one is that we also work on manifold learning methods that allow for example, the generation of new types of proteins by organizing latent spaces based on certain properties. Okay, that's concerning time, that's all I have to say about it, but please check out this paper, Pullback Flow Matching on Data Manifolds. Yeah, so the conclusion is, thanks Arnoud, I'll wrap up here and give the floor to Johannes. Okay, maybe this is the slide which I want to end up with, is that many of our research is focusing on the idea of compressing information to its geometric essence. We've seen some examples of this, but working with compressed latent representations, that's something, I think that's the future. And I think that's also maybe what Johannes is going to talk about, how to make things scalable by representing things in proper ways. Yeah, so let me stop right here.
Awesome. Thanks. So I think it was super clear presentation, super interesting presentation. Nevertheless, I hope there's still many questions to come. So this was Professor Beckers, and I'll actually switch almost to Professor Brandstetter. So a quick intro on Johannes Brandstetter. is so Johannes is an assistant professor at the Johannes Kepler University in Linz at the Institute of Machine Learning. And before he did his PhD studying Higgs boson decays at the CMS experiment at the Large Hadron Collider at CERN in Geneva, Switzerland. And he also works in the field of geometry, deep learning, and AI for science. So Johannes, the floor is yours.
Thank you. Can you hear me?
Yes.
Yeah, thanks for the nice introduction. Thanks for having me. It's always hard to give a talk after Eric because Eric is usually very good with visuals and slides and presenting. So I have to really ramp up my game here. My talk is a bit a different direction, or not a different direction. It's a direction which tries to bridge a gap between what is currently available in what we have in AI and how this could actually work or could actually be used in real world. So basically this comes from a desire I'm thinking about like approximately 3 years ago, because I also had some time in industry, and the question I'm trying to answer is how we get a similar effect as we see in language and computer vision in scientific and engineering applications. We all know the scaling curves. We all know that the data and parameters is all you need paradigm from LLMs. I think Eric explained in great detail how at some for some instances this is not holding up for science. For me, I very much think I like to think in the terms of language and in the terms of what can be expressed in languages. Although when you move to science, the language is not in tokens or is not in terms of text. The language is much more in terms of differential equations in all different kinds and all different forms, from stochastic differential equation, ordinary differential equation, partial differential equation, in all its complexities with all different terms. And basically, these differential equations describe the universe we know, from particle physics on the very left, which is described basically by Lagrangian formalism, from which you can get all these field equation, up to molecular dynamics, classical fluid dynamics, weather modeling, and up to astrophysics and Einstein's field equation in all its glory. There is a lot of focus, a lot of research going on in the left part, especially in the molecular modeling part. Also like highlighted by breakthroughs like AlphaFold. If you go a bit to the right, the AI contribution gets smaller and smaller. And if you want to visualize that in some sort of graphics, you can say something like that you have breakthroughs in language, that you have breakthroughs in computer vision, that you have some breakthroughs in natural sciences, but especially if you go more towards engineering, manufacturing, these breakthroughs get less and less. And the question I'm trying to answer, or I'm trying to show in this talk, is my personal opinion, what it really takes to make breakthroughs in these areas as well. And this is an unsolicited sammelsurium of my personal opinions, and I will basically share them with you by going through 3 different projects, 3 different works, highlighting what worked, highlighting what is not working, and highlighting where I think the future is going. I will talk about some multiphysics modeling of some large and complex system. I would talk about CFD, computational fluid dynamics, as you would use for automotive aerodynamics, and I will talk about molecular dynamics modeling. All 3 of them can be found in some way in this diagram I showed on the previous slide. So coming back to the scale is all you need, or scale is not all you need question. I personally think that there is a different axis to the scale. So there is not only the representation symmetry axis, but there's also the question of what scale means in engineering. Especially if we look at the data model scaling paradigm, which we know from LLMs so well. And if we start to think about real world use cases, and I will show you in a second a few of these examples, we basically are confronted with a problem that if you want, for example, to model an airplane, or if you want to model a high fidelity car simulation, you suddenly are confronted with simulations which run on huge meshes. And I'm talking about millions and sometimes even billions of mesh cells. And this represents a different scale of the problem for us as AI researchers, because we usually handle like images and videos which have this 256 times 256-ish dimension. Obviously, some of them are a bit larger. But compared to industrial scale fluid simulation, for example, this is like a tiny set of problem. Two scenarios here. This is a multiphysics simulation. I will talk about that in a minute. We will see like a million of particles bouncing around and interacting with the fluid component, which is also a couple of 100,000 mesh cells, and then they interact chaotically over time. Or if you want to get a step crazier, you can think of doing a classical simulation for such a Formula 1 racing car. So you want to predict, so to say, the flow fields around the car, the flow fields, the pressure field on this car. And in a way to do that, you would need to mesh the whole 3D volume, and then you would run CFD simulation on this volume to get some quantities. If you do that properly, and if you do that with state-of-the-art modeling techniques, you would quickly end up with a billion of mesh cells, which is very hard to do for numerics, but especially if you want to build AI models which do that presents a new challenge. Luckily, we have we are seeing some breakthroughs in this area, and for me, most notable, these breakthroughs are coming from weather modeling. And this is actually also where my journey started. So I was at the beginnings, I was part of this Aurora project, which you see here on the left, which is arguably the first foundation model of the Earth system. And doing this Aurora project, I basically learned two things which make weather modeling very distinct. First of all, the underlying data you have is actually better. In many cases, is better than what a solver can produce. Why? Because the data you have is corrected by the actual measurement, corrected by the actual weather. It's pre-processed, post-processed, so to say. And that means the neural network can actually overtake the numerics weather prediction, because they are just based on a numerics weather model, and nobody really knows what weather is doing. Secondly, the data dimensions, I just wrote down here the tensor type, if you would use that as a PyTorch object, of one data point, so one snapshot in time, no time component, of the era 5 data of a state of the system. And the dimensions here are huge. So this actually basically points down to the fact that we are actually having tools and having meaningful ways of how to process this large data. And that if we do that right, we get like extremely powerful models which overtake classical methods, both in accuracy but also speed. And that can really be used in real time for many different applications. So that was my motivation. But the problem is that if we think back to these Formula 1 cars and to the simulation, none of this stuff is happening on a nice regular grid as the weather modeling, which is basically happening on some, you can think of 2D image data if you stress it down to this. So we are dealing with three-dimensional manifolds, so three-dimensional complex grids. And we want to set the scene first, so that the object or the frameworks we are using, and basically it's the name of the game is using neural operators, which is a fancy terminology, a fancy framework for porting, for me personally, for porting computer vision tricks to physics and science and engineering models. What do I mean by physics tricks? You can think of a neural operator really as trying to match the underlying function and trying to map the underlying function forward in time or to any other condition. And matching an underlying function means that basically you should be invariant to the number of points you sample in the input and to where you sample this point. So if you, again, I stress the weather modeling, and you can think of, you have some weather station, the way you get the internal representation of the network should not matter of how many stations you have and where are they placed. Obviously, there is a limit in terms of what you can resolve. And similarly to the output should be continuous in basically how many points you're trying to decode. And this is basically the framework we're using, and we're using now to describe many different of these problems. But the first is that we have to overcome a few challenges. First, as I already said, the data, which is not listed here, the data is extremely big. But there is also that the input is extremely big in terms of mesh points. But there's also other challenges, like usually data is scarce, and by scarce data, I mean high fidelity data. So if you go to I don't know, Boeing, Airbus, or Formula One team, you wouldn't get a lot of high fidelity simulation because they are just very expensive to calculate for themselves. Another challenge is that there is no framework which exists for that. So you cannot just use a transformer and use on these meshes or on these large systems. I mean, you can, but good luck with self-attention of a billion of tokens. So you need some smarter ways. And obviously, the way to go forward is by latent space modeling. So that was basically the first first wave of architectures in that way. There's now many similar approaches from different groups over the world, which try to build latent space models which describe physics in a latent space. One of them was presented by Eric before. For me, latent space modeling means that you need a very flexible encoding, which works across resolutions, which works across basically settings, which works across geometries, across scenes, and you need a very flexible decoding. That is easier said than to be done. What I'm going to do next is I will very quickly outline how such an encoding looks like in a very let's say pragmatic manner. So I'm not explaining any technical details. I just explain concepts and then afterwards show how this is ported to different problems. Firstly, what we have, as I already said many times, we have a high dimensional input, and high dimensional means in terms of grid points, in terms of particles or whatnot. And one thing which is a difference between simulations we are using and the way neural network process data is that simulation need to be on a very fine mesh. Otherwise, if you look a bit into numerics, if the mesh is not very fine, and if the mesh is not like basically there is a clear law between the temporal and spatial updates, you quickly run out of outputs are quickly diverging. So what you can actually do to get basically the same representation, you can subsample heavily. So the subsampling is not only very well used for data augmentation, because you can sample different points and it should give you the same representation, but it also reduces the complexity of the input dramatically. That is something which can be applied to different degrees on various scenes. For example, we have problems where we can basically subsample 1% of the data. So we can throw away, in quotes, 99% of the data. Secondly, you can use something like a local aggregation step, very similar to patch embedding and vision transformer, selecting some sort of local champions, we call them supernodes, and processing information to the supernodes very much circumvents or very much lets us port information from local neighborhoods and aggregate them. And then we already have some kind of local champions. Again, this is very heavily subsampled compared to the original data. We can add some sort of position and embedding there, and we end up with something like a sequence, which we might compress further, and we have some sort of latent space where we can add all information about physics, boundary, and so on and so forth. Each of these steps can be done in arbitrary complexity and with arbitrary, so to say, using arbitrary tricks. But in the end, this is the essence of how we are scaling our approaches. One thing which is very neat is the neural field decoding. This is also something which was used in Eric's work presented before. It is really a new paradigm in this sort of modeling. Originally, I was first mentioned in the CVIT paper from University of Pennsylvania. And what this is basically doing, it represents the latent space as a condition, a conditional neural field, and the parameters are conditioned on this latent space, and it lets you encode the state of the system at arbitrary points in space and time. And this has two very, very nice benefits. The first is that the encoder and the decoder are decoupled, so that you can, for example, encode a geometry and predict physics around the geometry. And secondly, that you can scale this up, because this decoding can be done in parallel, so to say. So you can, just from a simple representation, decode a very, very complex large field. And these things are very, very handy. So let's have a look how we use that in practice. The first is this kind of multiphysics simulation, which I teased before. I have to say, this project started roughly 1.5 years ago, and it came. The reason for starting this project was that I approached some numerics experts, which are sitting here in Linz with us, like Thomas Lichtenecker, Stefan Birker. And I asked them what's one of the hardest problems you have, and where would you really impressed if you can model them with machine learning. And we came up with this multiphysics modeling. It's called multiphysics system. It's called fluidized beds. You have, if you just look on the upper row, you have two components. The one component is particles, which are bouncing around and interacting with each other, which is shown the particles only in the middle. And on the right, you have a air which is blown in from below, which makes this particle dance, so to say, and both of these simulations interact, or both of these systems interact with each other. That's why it's a multiphysics simulation. And the problem is that the number of particles is very, very large. So we're talking about 500,000 to 1 million particles, but we can scale this up arbitrarily. Secondly, this is a chaotic system. So that means if we start with different initial conditions, things very quickly get chaotic. It's a temporal system, so it's very hard to get this system stable. So how we approach that? First of all, we learned something important about representation. If you start modeling particles as particles and using, for example, a graph neural network, this is not scalable, and it's also very, very hard to get all interactions correctly. Because if any of these interactions is somehow modeled incorrectly, then the error starts to propagate. But it is much handier from a machine learning perspective to think of the whole system as like a bulk behavior, as like a material which is moving together. And you can start thinking of such system just as a field, which evolves. In that case, a displacement field, over particles, which is moving. And that is actually very, very easy to handle and very, very easy to train a neural network on. And you don't need 500,000 of nodes. No, you just need like one hidden state, which is able to decode the displacement vector in a certain geometry. Secondly, we have these two systems which interact with each other, the particles and the CFD components, so the air which is blown below. And here we use tricks from computer vision, in case we from diffusion models. Especially in diffusion models, you have also multimodalities which come up from text. You want to condition the model on and the vision part. So we call it multi-branch diffusion transformer, which combines these two modalities and basically makes the combination in the latent space by letting these modalities interact with each other. And then we decode different fields. And as I said, we cannot decode particles. That's why what you see on the lower part, on the lower left, so to say, in this GIF, you see that the isosurface or the surface where so the diffraction of the particles is under a certain threshold, dancing around, showing how the bubbles evolve, which is the correct description of particles dancing around in the upper part. One thing is, and that is very nice in the systems, that if the models are big enough, that there is enough data, those models really start to understand physics. Understand physics is a big stretch, but it's very interesting because what we really do is we do a next step modeling. So we just predict the next step as language model predict the next token, we predict the next step in a system. And what you see on the left is like a mixing ratio. This is how two type of particles mix over time, depending on different inflow velocities. It's a very, very complex system, very, very chaotic. And actually, if the input velocity gets higher, the system obviously gets harder to model. But it seems that this same paradigm of understanding or getting some trajectories correct is also preserved here. Although obviously there's things to improve. Okay, so to end this chapter here, I would let you guess which of these outputs is from a neural network and which is the actual simulation. To make life harder, we converted the simulation output also into these isosurfaces so that you cannot use the particle distinction per eye. I let you stare at it for 3 more seconds. The clue is that the neural network output is much smoother, so it's not able to get every detail correctly. And that is actually the left one is the neural network. So the learnings we are having from the system, I should probably also mention Benedikt Alkin, Tobias Kronlachner, and Samuele Papa, who did all this work and train all these models with great detail and lots of hard-working hours and weeks. The largest model we trained was roughly a 1 billion parameter model on a lot of data. Obviously, that was needed to get it to work. But still, we learned that these chaotic systems are super hard to model. And actually, that's definitely the frontier of the next research. What we also learned is that there's a lot of tricks from computer vision, like these multi-modal diffusion transformers, which you can actually use and which you can convert into this neural field paradigm. And last but not least, as I already said, field-based modeling is here to stay for us at least. The next project I'm talking about is now we're working with really huge meshes, as I showed before in the introduction. So with meshes of these automotive aerodynamics. Why automotive? Because in automotive we have we now have publicly available data. I will say about this more in a minute. Difference to the work I showed now is that these models or this task is now static. So you basically have a task where you have a geometry and the geometry is the input and some fields either on the geometry, that's the surface, or around the geometry, that's the volumetric prediction, are the output to the model. Geometry to surface or volumetric prediction. What I showed left is called the driver is from the driver ML dataset, a publicly available dataset from Neil Ashton and colleagues. There's also the driver net dataset from Mohamed El Rafi and colleagues. A shout out to those efforts. They are really extremely nice datasets to play around with. They allow us to really train complex objects. If we look at this DriveML dataset, we're talking about surface meshes of more than 8 million mesh cells, so only the surface alone, and volumetric mesh cells of more than 160 million mesh cells. So that's really a lot. And the challenge here is to give different geometry inputs, like for example, a cat geometry or different sample input geometries, put it into the neural network, and the neural network should be able to either decode the surface and all its nitty-gritty details, or give you even a volumetric prediction of the flow fields, vorticity fields, and so on and so forth. There is 2 results I want to highlight here, which excite me a lot. And one is, which is shown here, the discretization convergence. Discretization convergence means for me that if you have a neural field decoder, basically which gets a geometry and you can query the fields at arbitrary many points on the surface, for example, or on the volume, that at some point these predictions get consistent. What I mean with that, it's very nicely seen if you look at surface values prediction. So if you go to a car manufacturer, for example, all they are interested, or what they're really interested in are quantities like drag or lift coefficient. And what are drag or lift coefficient? Those are integrated quantities over the volume. But in order to get good drag and lift coefficients, or like near perfect drag or lift coefficients, for example, this DriveML dataset, you would need at least 4 million of these mesh points. And if you go with more mesh points, at some point, this drag and lift coefficient, they start to not change anymore. With the neural network, if we do this neural field decoding on the surface, we can actually, with 200,000 decoded points, we get like a pretty good estimate for the drag and lift coefficient, which is not improving anymore if we add more points. So the neural network is already able to capture the whole physics and give you a correct drag and lift coefficient if you only predict 200,000 points on the surface. But more importantly for me, if you increase that now to 8 million points on the surface, the lift drag and lift coefficient is not changing. That is very important because that means, so to say, that you have correctly modeled the underlying function. So the function is really independent of the points you sample whenever you have reached a critical mass. And by the way, the difference to 1 between the red between the two lines is because our model is not 100% perfect. So it makes a tiny error, which is obviously a training error because these models are not perfect. But the numbers they are getting are quite nice. The second thing which is extremely nice in this regard is transfer learning. So as I already said, we have 2 data sets. One data set has a lot of samples, but the numerical simulation you use to calculate the CFD model is of low fidelity, whereas the other data set, driver ML, is produced with high fidelity CFD model. So the turbulence model, which models all these behaviors between boundary layers and so on and so forth, is a very expensive model. So therefore, the data is high fidelity. The meshes are more finer and so on and so forth in order to depict this this high fidelity, or be able to run these high fidelity solvers. And here, between low fidelity and high fidelity data sets, which are quite different in terms of what physics you're using and what the data is looking like, you can see extremely cool transfer learning, so to say, settings, so that you can transfer a model from a low fidelity data to a high fidelity data, and you get like that the errors are basically the number of samples you need to train or to get the results is that they really only is half the sample size. You might now ask, the samples plotted here on the x-axis, they are really, the number is really small. So we're talking about 200 to 400 samples. That is because these geometries here the difference is not too much. So they're very similar. So the interpolation is not too hard. And more importantly, you can sample, as I already said, you can subsample a lot of input and output points. And with this subsampling, you can do an extremely heavy data augmentation, which helps to make these models actually pretty good on small sample sizes. So again, learnings here, this is where the decoupling of encoding and decoding is really handy to make surface to volumetric prediction, to make cut geometry to full surface models, and so on and so forth. It's actually very interesting to see that the data we need is not as much as we expect. Transfer learning can do a lot of tricks here. It's still super challenging. What's the best way of how to encode geometry, of how to tell the model what is actually looking at, or what is actually physically modeling. And we have not touched generative modeling here. So obviously you could then ask for certain flow behaviors you want to have, and you would ask for a geometry which models this flow behavior, or vice versa. So this is definitely interesting work in the future. And I want to close this talk with something a bit unexpected. So there is a lot of hype going on about this latent space modeling and about basically porting very complex phenomena to a latent space. What all these models have in common is that they have some sort of general bulk behavior, as I showed with the particles, which move around as a system, which I showed with the car, which basically describes the whole flow field as a system. But we have different types of data, and in that case, molecules, which have a very clear abstract representation with atoms and bonds, which cannot, or which is very hard to think of as a bulk behavior because we have this abstraction. But it turns out that latent space modeling also seems to work for some kind of molecules. And how? I will explain that. So the task of molecular dynamics is quite evolved. What you actually do, you have a molecule at time t, and you want to know how this molecule evolves forward in time. The problem is just that this is like a stochastic process because you follow some Large-Mohr dynamics. Because with all these effects from quantum mechanics, this turns out into a stochastic distribution. So you basically have a state of the system at time point t, and then the trajectory forward is like a probabilistic trajectory. So how you normally would model that is with some graph neural network, where you have the input graph, and this input graph you project forward via the fusion model or whatever into the future. That works, but if you want to do a latent space modeling, you run into problems, because if you somehow try to encode such a graph in a latent space, as I said before, you remove a lot of this structure. You especially remove the notion of nodes, the notion of connectivity, which is not very handy, because that's the essence of a molecule. On the other hand, we learned that the tricks from computer vision and especially latent space modeling is really what makes the system scalable. So credits to Florian Sestak here, who came up with this extremely nice idea and extremely nice algorithm of how to use an ID-based tracking in the latent space to keep the notion of atoms and to keep the notion of connections alive, and therefore allow a latent space modeling, even if the whole molecule is, so to say, compressed to this latent space, and things like connectivity and atoms get basically encoded or moved. So how does this work? Let's have a look. So we have our molecule aspirin as an example. We add some IDs. So the input token for this molecule would be the features, the position, and the ID. And then we design an encoder which takes these input tokens and maps them into a latent space. But it's very important that the dimension of the latent space stays constant, because if you get different molecules, larger molecules, you need the same latent space representation, because in this latent space we will train a generative model. And the way we train this generative model is that we get one part of the tokens from the encoder, and the second part we populate with mask tokens, which we use a standard normal to initialize them, and then we run a flow matching process in the latent space. And then we do something very interesting. We are querying this latent space. You can think of this querying of the latent space again as a neural field, but we are not querying it with positions, but we're querying it with IDs. And what we get back is the position of the atoms. So in that case, we basically keep the number of atoms, because the ID represents the atoms, and the querying of these atoms allows us to retrieve where these atoms are, or how these atoms move, so to say, probabilistically with respect to time evolution. Just to show some nice visualization. I'm not showing tables of bold numbers, because these you can also check in the paper. But the very cool thing about this is that you can model different types of systems. So basketball players on the left, how they probabilistically evolve over time, or molecular dynamics of different smaller and larger molecules on the right, how the trajectories evolve over time. For more information and basically more performance comparisons, please have a look at the paper. What I really like is that this is an approach which basically works out of the box for any type of these dynamical systems, and it doesn't need a lot of bias, and it basically doesn't need to be tailored towards certain angles or certain structures which you need to encode. It works for different type of dynamical systems, which I think is pretty neat. So I was very impressed by the outcome, which I wouldn't have thought that with latent space modeling, that's a bit an overstatement probably, but with latent space modeling, you can actually even model molecules, which I was not very convinced. Again, we used a lot of tricks from computer vision to scale this up. And it seems that this latent space modeling works very well for generative tasks here. And what I want to conclude here, that the molecules I showed here are rather small compared to the tasks or the images I showed in the beginning. So that's actually not really a compression, but much more like an enhanced latent space. So that's something which one has to keep in mind. And that's actually brings me to the end of the slide. What I really like is what my passion is, to go to large systems. I think large systems are extremely challenging, but we have the tools now and they are not out of reach. And it's I think the time for having impact on these large scale tasks. There's lots of problems to overcome. I think I showed and mentioned you a few. The modeling paradigm we're using so far is an encoder, latent space approximator, and decoder approach. The decoder is a neural field. The encoder is a vast compression engine, so to say. But I also have to say that we've not gone the full circle. So none of this is physics informed. So basically none of these field predictions have like mass conservation or divergence free or even respect symmetries. But that's not saying that this is not work in progress. So this is not something we are adding. Definitely, I think that this is the way to go. The simple reason here, it's just very, very challenging to get those systems to work, and we do our homework first. What I really like, or what I'm really starting to be a big believer, is to detach oneself from a different, or from any specific method, but to attach oneself to a problem. And as such, I really like to detach myself to large problems, and I use any tools necessary to solve those problems. Personally, I find a lot of these tools available in computer vision. So really big credits to the vision community. And this is basically coming me to an end, and I want to thank everyone for having me here.
Awesome. Thanks, Johannes, for the great talk and also the interesting insight at the end of the not large solutions, but large problems where you had already experience at the Large Hadron Collider, for example. So really good closure. So now I think we move on to questions and answers, if any.
Do you mind if I start off the question to Johannes? Just curious, Johannes, what do you think? You mentioned several things that could sort of explain why things work so well in this neural field setting. Like I think you mentioned something modeling things on a bulk level, but at the QM9 or sorry, the molecule stuff, you say, well, these are small molecules, so it's not really compression. I was thinking, is it really like that these neural fields, they act as some sort of renderer that sort of discards any noise or any kind of instabilities because you have some latent and you render it into the thing that you want? And you think this is like a main contributing factor to the success of these neural field methods?
I think there are many options, many points. So first of all, with these neural fields, you can basically do, if you have transient systems, a system which evolve over time, you can really use a two-stage approach, right? You can train encoder, decoder first, and then train the approximator in the middle, which we know basically, which I think the community has figured out how to do. Secondly, I think as well that this decoder is kind of a denoiser because it really forces the model to concentrate on different outputs and forces the latent space to somehow have a correct representation. And you can do many different multi-learning tasks on that in order to force that. I'm a big fan because of the parallelization, to be honest. I think that's the only way how to go. In the encoder, you can do many different things, and we are by far not reached the maximum here. But the decoder, I think this is really the only way to go.
Okay, cool. Yeah, I have actually many questions, but I don't know. Maybe I'm just wondering. Let's prioritize on audience if there's any.
Yeah, no, there's no audience questions yet, so I'll let you rank your questions by importance and go with the most important one first. Eric.
Okay, then Johannes and I have a discussion. But please, if there's any from the audience, just interrupt us. I'm just curious about Johannes, about how do you see the role of generative modeling in these paradigms? Because what we're currently working towards is, well, we have generative models on latent space, and this is nice. So we can kind of characterize this latent space in a statistical sense. And we could subsequently utilize this to act as priors, right, in our inference and in our encoding steps. And you mentioned something about diffusion models in one of these later models. And I'm just wondering, like, what role was the diffusion model playing there?
Yeah, that's a very good question. So first of all, for the molecule setting, you have this basically this setting that you have a state of the system, and you want to predict the state of the system forward in time. So you basically want to generate and since it's a stochastic process, you want to generate a distribution depending on the input time point, and that's a very much where generative models are very good. And that's why here I would say. So basically, the flow matching model we used is kind of the same flow matching models others used, but we didn't use it on graphs. We use it in the latent space. So that's
Okay.
I think the standard setting of how generative models are used.
So maybe just if I understand correctly, so you use it really for next time point prediction. Like
Yes.
you consider a distribution
Yeah.
delta t ahead of time.
Yeah.
Okay. Yeah.
Exactly. And there is also other aspects of especially diffusion models, and that is this refinement perspective. So it turns out you see more and more works that especially in this physics system where you have all these different frequencies, you cannot capture all scales correctly accurately with a one-shot prediction. And there's actually not a good objective which forces the model to do that, because the weight of lower frequencies is just much higher than the weight of higher frequencies. And so there is this iterative process that in the end, the diffusion model is an RNN in frequency space, right? And that you can use this sort of refinement to get a better physics understanding, a better grounding in the frequency space, which is not so different to what you explained actually.
Yeah, okay. No, I can relate to this. We didn't make it that explicit, and so we're sort of making baby steps in the generative model. We kind of focus more on, for example, where we can flow matching on different type of manifolds, precisely because if you want to change the latent space to a hypersphere or a torus or whatever, then we want to know how to do this efficiently and properly. So that's kind of the level that we're at, but not so much in the forecasting. Yeah. Okay, but this is nice to hear. I wonder, like, is this still sort of like the next time point, next token prediction kind of paradigm, or do you think and that's sufficient, or do you think there's a need to have sort of flexible, like, okay, let's predict right away what the system looked like 10 seconds ahead of time? Because it depends on the type of simulations, of course, but the reason I'm asking is because I have medical data with time follow-ups, and that also follows some sort of dynamical system that is conditional to the state of the patient. But kind of often we talk about, okay, what does it look like 1 week or 1 year ahead of time? And then, so I just wonder, what can you do in the absence of like really dense time?
That's a very, very good point. So in this, that's actually a discussion I had a lot with Daniel Worrell a couple of years ago. There's this Courant-Friedrich-Levy condition in PDEs, right? So where you relate that the step size and time in space versus the step size and time.
Yeah.
You can always argue that if you compress the system, you can also make larger steps in this compressed space. But obviously there is a certain threshold at which the predictions just get noisy. And I mean, we saw that in weather modeling. You cannot predict 2 days ahead one shot. But for that, you need to do it, let's say, stepwise. But it's also if you do like tiny time steps, errors accumulate, and so to say, trajectories diverge, and basically you move away from the true trajectory. And that is, I think, a correct autoregressive modeling is still something which is not clearly solved. I mean, there's people start to acknowledge that and start to come up with solutions. I think this is also something where some better grounding might really help.
I see. Yeah, but maybe also maybe to answer like what just came up in my mind, you talked about stochasticity and stochastic or chaotic systems a lot, right? So in that sense, maybe it's just impossible to predict too far ahead in time, right? So that's also yeah.
Still, if the system is chaotic, you cannot do it, but still you want to get the statistics right. Yeah.
Right.
So it's mixing behavior. You still want to get the mixing rate right, even if the trajectory diverges.
Yeah. All right, cool.
And I don't know how you see it, but I start to see more and more that this pre-training which people are doing is something like some prior, but then when you really have to solve different tasks, maybe then you can bake in the guarantees either with a soft constraint or a hard constraint.
Yeah, no, I think indeed, like the starting point is that you should be able to scale, right? And you will make certain errors, though I think this paradigm of working with latent variables kind of filters out some class of errors, just because, well, it acts as a renderer or as a protection method to a solution space. But yeah, so maybe that's my question to you. Like, did you run so far into like crazy equivariance errors, or like the things just don't make sense, or maybe at the scale that you look at, if you want to compute some summary statistics from the dynamics, then they don't matter really.
Yeah, but I don't know if Samuele is in the audience, but he can tell you how hard it was to get this mixing work. So this was, I think, the hardest problem we solved in a chaotic system. Is really, really, really hard. But just because the problem was not, there was no recipe how to do that, right? So you had to play a lot around with how to encode this and what patching you use and so on and so forth. At the moment when the network really started to learn and the loss really got down, the physics was also correct. I would say that in these examples I'm showing here, it's harder to get the loss, to really get the network, let's say, overfit or understand understand is a hard word, or to be able to model the data. And if so, it also models the physics quite okay-ish. I would not say perfectly, but quite okay-ish. But obviously the next step would be to be really reliable and so on and so forth. But in these, and that's what was kind of the point I was trying to make. The first thing is to really get the models, the loss down, which was
Yeah,
hard.
no, that's a big win. Yeah, nice. Yeah.
So we have a private session here. Which is always
Yes,
nice.
actually, we are almost complete. So I think it was interesting presentations and also now interesting discussion by leading scholars in the field. In fact, an Alice scholar and an Alice member, which we're super happy about. So I think this is the end of our session, and I think there's a small outro by AI for Good, which I'll let now play.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.